apparently I can't stop doing Lagrangian problems. So this one I actually have a demo for. So this is the chain on the table problem. So here's a chain. See, I actually have a chain. And it's hanging over a table like that. Maybe you can't see too well. And I'm going to let it go, and then it's going to fall down. Now, we're going to model this in a wrong way because it's actually more complicated than what I imagine it to be. But then maybe I'll make a better model numerically. But I don't know. Can't promise stuff I don't do. But let's just do the Lagrangian problem. So here I have a chain of length r, and I didn't use L. Hopefully you know why I didn't use L for the length of that chain. And it has a mass m. And then there's some bit of it hanging over the table. And we want to find the motion of this whole thing. So this one's a little bit different because although it's just 1 degree of freedom, right? How far is that hanging down below the table? The mass is like, there's like 2 objects that are moving and they have different masses. So there's that. Let's just get into it. Let's just draw what we know and start using the Lagrangian equation. So let me go ahead and say this. I'm going to first calculate the linear density of the chain. So lambda is the linear density. It's the total mass divided by the total length. Because I'm going to need that, right? I'm going to need to know what's the mass of this thing, what's the mass of that thing, and it depends on their position. So also, I'm going to call this y, and I'm going to call this x. Okay, so my x coordinate is over here. It actually has a negative value, and the y value has a but it's the end. It's the ends of the chain. Okay, so with that, I can say, I know my constraint is that x and y have to add up to be equal to the length of the chain. So I'm going to write this as x is r minus y negative, right? Because y has a negative value. And it should be plus. No, let's just call this s. I'm going to call that a positive value s. Yeah, s, like that. Okay, so s is the distance down. So that's going to be in a positive direction. So s is going to get larger as that falls. So that means x is going to be less and less negative. So that's good. That's my real x value. So I'm going to need that to animate it. You knew I was going to animate this. You knew that. Okay. So then y would be negative s, right? That's my actual y value right there. And again, I'm going to need that to find the thing. Let's go ahead and write the kinetic energy. So the kinetic energy term is going to be 1/2 m1 x dot squared plus 1/2 m2 y dot squared. So this assumes that this is the mass m1 and this is the mass m2. And m1 only moves in the x direction, m2 only moves in the y direction. But m1 and m2 are not constant. I told you that. Okay. So let's just find these derivatives first, and then we'll find an expression for m1 and m2. That's not too hard. X dot is going to be equal to the derivative of this, which is going to be s dot, right? Because I have negative r, and then I have plus s, and I take the derivative of that. R is constant, so it goes away. And then y dot is going to be equal to negative s dot. Again, that's a pretty easy derivative to take. Now what about m1? So m1 is going to be this length, which has a value of x, which has a value of r, a length of r minus s, times the linear density. So m1 is going to be r minus s lambda. And then m2 is just going to be lambda times s, because it's the length of that. So let's put that all together and write my kinetic energy term. T is 1/2 m1, which is this, r minus s lambda, times x dot, which is just s dot squared. And then I have plus 1/2 m2 times, mass 2 is lambda s times negative s dot squared, because we'd square that, so it's just s dot squared. Okay, let's just go ahead and simplify this, because you never know if you're going to get a little nice bonus from simplifying it, and you do. So this is going to be, I'm going to just multiply this out, 1/2 r lambda s dot squared, that's this term, minus 1/2 lambda s s dot squared plus 1/2 lambda s dot squared. Oh my goodness, look at that. Boom, boom, they cancel. And so that's my kinetic energy term. And it actually makes sense. I'm going to write over here. T is 1/2 r lambda s dot squared. Think about the whole chain, right? That chain, the speed of this chain and the speed of that chain are the same. So they have the same speed. So I can really think of it as just one object that has a total mass m, which is lambda times r times s dot squared. And so that makes sense, right? So this is just the kinetic energy term. We don't have those other terms over there because the change in mass of this is equal to the opposite of the change in mass of that, and that's why those two cancel. Okay, now what about the potential energy? Let's write down the potential energy. If I call this my y equals 0, then that chain on the table has 0 potential energy. That makes sense. Now what about this part right here? Well, it's not mgy in this case. It's not m2gy. It's mgs over 2, right? Because I need to find the center of mass of this. So as this thing moves down, the center of mass moves, but it's a little bit different. So u is going to be equal to negative m2, which is going to be s lambda g times s over 2. So that's my negative y value. That's my negative y value of the center mass. And then that's my mass of my center mass, right? Let's double check because I made a mistake on this before. Yes. So this is going to be negative 1/2 lambda g s squared. So now I can put it all together with my Lagrangian, which I'll write up here so I have more room. L is t minus u, so it's going to be 1/2 r lambda s dot squared minus the potential, so plus, I'm still in there, okay, plus 1/2 lambda g s squared. So now I have 1 degree of freedom. I can use the Euler-Lagrange equation, which says the partial of L with respect to s minus the time derivative of the partial of L with respect to s dot is equal to 0. That's a dot. Okay, so let's just do it. We always do this. Let's start with this part right here. I'm going to calculate that, the partial of L with respect to s. Okay, I'm scanning through here. I'm looking for s's. That's an s dot, doesn't count. There's an s. So I have to take the partial of this with respect to s. It's just going to be, the 2 comes down, I get lambda gs. Okay. Now let's do this. The partial of L with respect to s dot. Okay, again, I have a pretty easy Lagrangian, right? So I just have that term, so it's just going to be equal to r lambda s dot, and then I can take the derivative with respect to time. There's only one time-dependent term, and that's s dot, so I just get s double dot. So now this has to be equal to that, so I can say r lambda s double dot lambda gs, right? Those two are equal because they're subtracted and they give 0. So that has to be true. Lambda cancels. It doesn't matter about the linear density of the chain, which kind of makes sense, right? It's a proportional thing. But it does depend on the length and it does depend on g. So I can write s double dot is equal to g over r s. And that's my differential equation. But wait. We can solve that. Right, that's a solvable differential equation if we make a little bit of some guesses and stuff. Okay, so you could do that numerically, but I'm going to solve it fully because I think it'll be fun. Right, it'll be fun. Okay, so I'm going to write this over here. S double dot equals G over R S. That's my differential equation. And in fact, I'm going to do this. Okay, so how can we solve that equation? Now, there's a lot of ways to solve differential equations, but the physics way is to say, okay, I'm just going to try to guess a solution, right? And I can use my vast experience of guessing to just come up with something. So here, this says that if I take the second derivative of the function s, I get the same function back with a constant. So what functions do that? And you can say, oh, cosine and sine. But no, those give you back the same function with a negative sign. So if I had negative there, this would be a simple harmonic oscillation, which is good that it's not, because we don't expect that chain to oscillate back and forth like that. That doesn't make sense. There's another function where you take the derivative of twice and you get the same thing back, and that's an exponential. So this could be, let's just guess that this is the following. I'm going to say s as a function of t is equal to a e to the bt plus b e to the negative bt. So now let's just take the derivatives and see if it works. So s dot as a function of t is going to be equal to a b e to the bt minus b b e to the negative bt. So that b is just a constant, and we'll find that out in just a second. And then the second derivative, s double dot as a function of t, is going to be equal to a b squared e to the bt plus b squared e to the bt. I like that, e to the bt. It just sounds nice, doesn't it? Okay. Well, this is b squared times s as a function of t, right? Because I got it back. So that's true if what? If what? If what? If b squared is g over r, or b is the square root of g over r. So I have my solution, but I don't have the constants a and b. So I need to find a and capital B right there, but that's going to work. Okay, so I have a second order differential equation. I'm going to need two constants. Those are my two constants. And so I need two initial conditions. So let's say that at t equals 0, s of 0 is s0, and s dot of 0 is 0. So I'm going to hang it down some piece right here, and I'm going to release it from rest. So if s of 0 is s0, I can plug it up here and say s of 0 is a e to the 0 plus b e to the 0. So that's a plus b equals s0. Okay, but I don't know a and I don't know b, but I do know that a plus b is 0. Now let's do the velocity. S dot of 0 is going to be equal to a b e to the 0, which is 1, minus b e to the 0, which is just 1, and that's 0. So from here, I get that a is equal to b. So if a and b are equal and they add up to s0, then a is s0 over 2 and b is s0 over 2. So I think I have my solution. S as a function of t is going to be equal to s0 over 2 e to the bt minus e to the negative bt. Did it. But of course, we want to animate it, right? You know, because I want to animate it, it's going to be fun, and it's kind of like an art thing. So if you're like, I don't even care, la, 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 don't want to hear about animations, then that's fine. Thank you for watching. But for those of you that want to do it, stay tuned, because now we're going to do it. Okay, now I do want to go ahead and point out something that's, I do need these, right? Because I'm going to need real x and y values. And I'm going to need a chain, and I'm going to need a table. And I'm actually going to use two chains. So here's what I'm going to do. I'm going to keep this. I'm going to delete this stuff. This is called eraser delete. I'm erasering deleting. So let's just draw out what we have here. I'm going to make a table. And this table is going to be a length LT for length of the table, and a height HT for the height of the table. Because if I make a box, a 3D box in WebVPython, it wants the dimensions, but it also wants the position of the center. Now, I want this point right here to be the origin, so that I can have my chain, which is going to be a cylinder. It's going to be 2 cylinders, like that. Okay. So if this is LT, HT, and this is my xy plane, then this position is going to be equal to the vector. I'll write it as a vector. Negative LT over 2, negative HT over 2, 0. So z is the 0 direction. And the other thing is that will put the top of this right at the origin, and then so my chain, if I want it to just be at x equals or y equals 0, I might need to shift that down a little bit, but we'll play around with it. The other thing I want to point out is a cylinder in WebVPython has two properties, right? Here's my cylinder. It has more than that, but it has two important properties. It has the position, which is the vector location of one end, and then the axis is a vector from there to there. So I'm going to put both of my positions for my chains right here at the origin, and then I'll have the axis for that one going that way, and the axis for that one going that way. And then every time I can just change, once I know the length, right? I can change over time the length of these things and see what happens. So that's what we're going to do. Okay, and again, I'm going to need some values and stuff like that. But jumping into Python, I know you've been waiting. Let's just do it. Okay, so I need some constants. G is 9.8. R is the length of my chain is 1. The mass of the chain I don't technically need, but I'm going to put it in there anyway. I don't know why I'm putting it in there. It doesn't even matter. Okay, let's see. My S0 is 0.1. That's just how much chain's going to be hanging off. You can change that, and we can change that too. I need my x. X is going to be negative r minus s, which I don't have. S. I'm going to use the S0 for my function, okay? And then y is negative s, lowercase s. LT is, what did I use before? 1, and HT is 0.1. Okay, let's just make our table, one thing at a time. Table is a box. The position is going to be equal to vector, like I said, negative LT over 2, 8 negative HT over 2, 0. And then the size is a vector, which you can't even see because of my big old head. Okay, right there. So the size is going to be equal to vector LT, HT. And then how much do I want it in the z direction? Let's just make it twice the height in the z direction. It won't really matter like that. Let's just run it and see what happens. And there's my box. Okay, I want to go ahead and put, my chain's going to be yellow. I want to put a sphere at the origin because those two cylinders aren't going to match up. So I'm going to have a sphere that's kind of like the middle point. And I'm going to point out, don't let me forget, I told you there was a problem with this problem. And I'm going to tell you what that is in just a second. So let's add that I'll call it the pivot. Pivot is a sphere. Position is vector 0, 0, 0. I want it to be at the origin. The radius is going to be the radius of the chain. I haven't decided that yet. Actually, I did it before. I had it a radius of 0.02, 0.02, and color is color.yellow. And let's just run that. So I think I need to move my table a little bit. I mean, I think it's okay. Let's move it down a little bit. So by 0.1 over by 0.01, 0.01, because that will shift it just perfectly. So my table is going to be minus 0.01, minus 0.01. And this is just, if you didn't do this, it's fine, right? But suppose you're making a textbook. That looks better. Okay. Now I'm going to make my chain 1 and chain 2. So chain 1 is going to be on the top. It's going to be a cylinder. Its position is going to be vector 0, 0, 0. Its axis is going to be vector x 0, 0. Radius is 0.002. Color equals color.yellow. Okay, run that. Yeah, and you see how I have that sphere at the end, so that it kind of looks like it's hanging over the edge. So now I can put chain 2. This is exciting because it kind of, it's not a super difficult Lagrangian problem, right? It's not that bad. Let's just copy chain 1 and call it chain 2. Position's the same. The only thing difference is the axis is going to be in the negative y direction. So this is going to be 0, y. I think that should be it. Of course, we're going to run it. Look at that. Kind of excited. Look at that. It really bent over nice too. Okay, we're all set. I mean, this is not a hard animation. The hard part was the table. So I need a time, t equals 0. dt is 0.01. Now, notice that since I have a full solution, I'm not doing a numerical solution, I can do any time step I want. I could do time steps of 1 and it would work. I know where it is. Okay. So let's just say, and I will give some homework after this because I just thought of another problem. Let's do while t is less than 1. Okay. So I always like to start off with a time loop because I want to do it as long as the chain's even partly on the table. But if you make a mistake with that, it's going to go on forever, and then you look silly. So that's fine. So the first thing I'm going to do is to calculate. Oh, I need my b value. I'm going to put b up here. B is the square root of g over r. Oh, I didn't even look at to check and see if that solution was valid or not. Okay, I can do that. Yeah, we got a bunch of stuff to do. I kind of was excited to get to this. So I can calculate S. S is going to be equal to S0 over 2, so 0.5 times S0 times exponential of b times t plus exponential of negative b times t. Now that I have that, I can copy this. I need to recalculate x and y. And then, now I need to move my chain. So chain 1 dot axis is equal to vector x0, 0. It's the same thing, right? But now I've changed my x value, so I need to update that. I don't need to move the position because the position's staying right there at the origin. Chain 2 dot axis is vector 0, y, 0. Now, the important part, update time, t equals t plus dt. Let's just run it. Okay, falling. Okay, so the chain went over because I'm telling it negative s, and the s got larger, so it made it negative x in positive directions. It doesn't know how to do. So let's just see if we can make it run until s is less than r. So it should work now. As long as s is less than r, then it'll just stop, because then the chain's all the way over, and it's not the same problem. You could keep on modeling it after that and just have it fall straight down. Okay. That's a win right there. I'm pretty excited with that. You could plot the position as a function of time and all that stuff, but I'm pretty sure that's good. Let's go to the board. I want to point out some very important things, some homework, some limiting cases, and stuff like that. And then you'll be excused. Okay, so here we are. So number 1, this problem, my solution's wrong. It's wrong. Okay, because imagine this chain is increasing in speed this way, or imagine the momentum at the beginning. The momentum at the beginning is 0, right? So as this chain is falling, and as this thing accelerates down, this part's pulling it that way, so this part's increasing momentum in the x direction. So the result is that it wouldn't just go like that. It would go like that. It would fall. It would start falling off the table that way, right? And that's kind of cool. But we forced it to go straight down. So it's how we have like a little a curved piece right here that's forcing it to go down. And that's fine too. Oh, the limiting cases. So does this solution even work, right? More importantly, does this solution work? Because what if S is equal to R? What if we have the whole chain over here off the table? If S is equal to R, then I get the acceleration is g. Free fall. That worked, and it's kind of exciting. What if S is equal to 0? So here's the case where the whole chain's on the table. There's no piece hanging over. If no piece is hanging over and S is 0, the acceleration is 0. That makes sense too. Okay. So here's your one homework problem if you need some homework to do for this. How long does it take the chain to fall off the table, and how fast is it going? Now, let me point out another way if you want to solve this problem, just for fun, because I don't know why. There's a very similar problem, the half-Atwood machine. I don't know why it's called a machine. So in this case, I have a mass connected to a string connected to another mass hanging down there. And you can solve this problem many different ways. The way I like to do it is say, okay, there's a gravitational force m2g pulling down on that, and then there's a tension, but this mass, this gravitational force on that mass is what accelerates the whole system. So in one dimension, you can say the net force is m2g, and that's equal to m1 plus m2a. So the whole thing is accelerating. That's the easy way of doing it. I do that in lab just because this is kind of a hard problem for algebra students to solve, but we just do it that way. So one thing you could do is to use the same solution and do a numerical solution where you say, okay, but now mass 2 is not constant. Mass 2 does depend on the height, and this mass depends on that height. So you can solve for the acceleration as m2g over m1 plus m2, but now you can say m2 is equal to the same thing that we had before, lambda times s, let's call that s, and m1 is lambda times r minus s, and then you get an equation that the acceleration is not constant, and you can solve it numerically by saying, okay, in a small time interval, v is delta t over delta v over delta t, and then s or v is delta s over delta t. And you should be able to get the same solution, but you could plot it right next to the other solution. Okay, finally, I did say that there's another way to solve the chain, and I don't know that I'll do it, but imagine a bunch of masses, so it's actually a real chain like that, but they're all connected by springs. And then I can just calculate the net force on each one. And so if it's hanging over the table, they have a gravitational force. If it's not over the table, it doesn't have a gravitational force. And then we can model it. And we should be able to see that the end whips out like that, like I said. I might do that. I'm not sure how hard it'll be. But that's that. Hope you had a good time. Link to the code down below. Link to the playlist for all my classical mechanics videos for this semester down below. That's it. Bye. Talk to you later.